Yesterday we were discussing about how we can model a system using differential equation modeling. So then we started talking about transfer function before we got interrupted by this power problem. So before moving into, so now we will talk about the second type of modeling that that can be used to represent a system, that is known as the transfer function modeling. But before moving into the transfer function modeling, I'll give you a brief, like we'll revisit little bit about our mathematics and all, because those things will be necessary while we are dealing with different kinds of transfer functions. Okay, so first of all, we'll just talk a little bit about this Laplace transform. So you all have studied this Laplace transform. So this Laplace transform means it decomposes. So this is basically if you have a time domain signal. So basically what we do using Laplace transform is that we convert the signal from the time domain into a frequency domain. So by using Laplace transform, it decomposes the signals which are present in time domain into a domain which consists of both sinusoidal functions as well as the exponential functions. And the domain of Laplace transform is usually known as the S domain. Okay, and S is basically nothing but S is a complex number and S is given by sigma plus j omega. So now this sigma plus, so if you write the equation of e to the power st, then S you can represent by e to the power sigma plus j omega t, and you can divide or you can expand this equation or this term into e to the power sigma t multiplied by e to the power j omega t can be written as cos omega t plus j sin omega t. So now if you write the Laplace transform or the definition of Laplace transform, so Laplace transform of xt will give you, is denoted by capital X of S, and it is defined as integral from 0 to infinity xt e to the power minus st dt. So this is basically the definition of the Laplace transform. And these are some of like the very basic if you take different functions, like here you have xt is my function. So if you have different values of xt, if xt is equals to, let's say, 1, in that case your Laplace transform will be equals to 1 by s. Similarly, if your value of xt is equals to e to the power at, then the corresponding Laplace transform is 1 by s minus a, and so on and so forth. You can I think you already know how to derive the equations, but you can still try to revisit these things, and you can replace xt with these functions, and then try to come up with the corresponding Laplace transform of that function. So these are some things which you would need to remember, and while doing more and more calculations, these things will come into play. So now another important thing about the Laplace transform are there are certain properties of Laplace transform which are very useful while doing analysis. So first of all, the main important property is that multiplication by constant. So if the function time domain function that is given to you is ft, then and if you multiply it with a constant k, then in the Laplace domain also it will just be reflected as a multiplication of that constant factor. So k of ft, the Laplace transform of that will be equals to k of fs. Now this Laplace transform, this is basically this satisfies the linear, it is a linear equation, so it satisfies the superposition theorem, you can say. So if you have k1 f1t plus k2 f2t, then in the Laplace domain also it will just be k1 f1s plus k2 of f2s. Similarly, you have different other properties like time scaling, wherein if you have a function f of at, where a is a real value greater than 0, then in the Laplace domain it will be transformed as 1 by a f of s by a. So and so on and so forth. There are other different kinds of shifting or time shifting, frequency shifting. Then when you are dealing with the first order derivative, if you have your function is, let's say, dx dt or df dt, then the Laplace transform is given by s into fs minus f of 0 minus. So that means you need to know the initial condition in order to figure out the Laplace transform. If the initial conditions are 0, then the Laplace transform of this first order derivative will be just s of fs. Similarly, for a second order derivative, it will be s square fs minus s f of 0 minus f dash of 0 minus. Now, if your initial conditions are zeros, then the time derivative, if you have a second order derivative, the Laplace transform of that second order derivative will be just s square into fs. Similarly, for integral, you have the Laplace transform of integral of ft dt will be equals to 1 by s of fs, and so on and so forth. So you can just go through the tables of so the previous table as well as this table in order to know, or in order to go through like what are the different properties of the Laplace transform which are there. Now there are two more theorems which are very important. So one is the initial value theorem. So what does this initial value theorem say? It says that if you take the limit of a given time varying function xt, the limit as t tends to 0, and so the limit of t tends to 0 of xt is equal to limit of s tends to infinity s of xs. So this is how using the initial value theorem, the time domain signal is related to the frequency domain signal. But you have to make sure that this initial value theorem is only applicable if the Laplace transform at the limit at x equal s tending to infinity that exists. If at s tends to infinity the value of this xs is undefined, or this does not exist, then the initial value theorem will not be applicable. Similarly, for a final value theorem, we will be dealing with limit t when final value theorem means as we are approaching t is approaching infinity, at that point, so limit t tends to infinity xt will be equals to limit s tends to 0 s into xs. And similarly here also this final value theorem will hold true only if the Laplace transform as well as the limit exists as s is tending to 0. So these are the two theorems which will be so later on when we are dealing with a control system and we need to see what is the steady state error in a control system and all. In those cases, this final value theorem is very much useful. So now talking about transfer function. So the transfer function, this we were talking about this yesterday. So transfer function is basically defined as the ratio of the Laplace transform of the output variable to the Laplace transform of the input variable. But the main assumption is that all the initial conditions are assumed to be 0. So now if you have, let us say if you have a system, some system you have, the input to the system is, let's say, xt, and the output of the system is yt. So this is in the time domain representation, and this is, let's say, a linear time invariant system. So if this is the case, then if you take the Laplace transform of xt, so that you can represent it by xs, and for the output it will be ys. So if you take the ratio of ys by xs, that will give you the transfer function of this linear time invariant system. And also you can we can define, or in other words, you can define transfer function as it is the Laplace transform of the impulse response of an linear time invariant system with 0 initial condition. Why do we say a linear impulse response? Because impulse means what? Xt is given by delta t. Xt is equals to delta t means that at t equals to 0, only at that instant xt is having a value of 1, and at all other values of t greater than 0, less than 0, at all other conditions, the value of xt is equals to 0. Now, if you take the Laplace transform of this impulse signal xt, so then that gives you that xs will be equals to 1. Now, if you substitute xs equals to 1 in this equation, then you see that gs will be equals to ys. So from here you can say that if you have a system, a linear time invariant system is there, and you are providing an impulse input to that system. So whatever output you are getting, if you are taking the Laplace transform of that output, that will be nothing but the transfer function of the system. Okay. So now we will talk a little bit about what is a time domain signal and what is a frequency domain signal. So basically, when you are representing a signal in time domain, so in time domain, the representation, it shows how the signal is changing with time. Okay, so let us say that you have a function sine of t plus pi by 3 plus 2 sine 2t. Okay, so then if you plot the a graph for this sinusoidal function, then in the time domain, what it shows is that you will plot the, so if let's say this is equals to some x, let us say this is some xt, or let us say this is xt. So then in the x-axis you will have time, and in the y-axis you will plot the value of the xt. So you will substitute for different instance of time, for different values of t, you will find out what is the overall magnitude of this function, and you will plot, and you will see that how the function is actually varying with each and every time instant. But when you move into a frequency domain, so in frequency domain, it shows, if you see a frequency domain representation of a function, then it shows that how much of the signal you have with each frequency. So in frequency domain, obviously as the name suggests, that the x-axis will be, instead of time, it will be frequency, and in the y-axis you will get two parameters. One is will be the magnitude of the function, and the second one will be the phase of the function. So in a frequency domain, the signal is represented by a sum of the sinusoids of different frequencies. So you have the frequency either in terms of omega, which is the angular frequency, or you can represent it in terms of f also, and each frequency will correspond to a specific magnitude as well as a specific phase. So if you take the example of this here, in this case you have sine t plus, so so in general you can represent a sinusoidal wave, a sinusoidal signal as a sine omega t plus phi. So this is a general representation. So if you compare this general representation with these, so there are two terms here. One is sine t plus pi by 3. So here you see that omega is equals to 1 and the value of a is equals to 1. And omega equals to 1 means f equals to 1 by 2 pi. Okay, and the amplitude at omega equals to 1 is 1 because this is 1, and the phase will be equals to nothing but pi by 3. Okay, so now so this is the first term, and if you look into the second term, so the second term is basically 2 sine 2t. So here 2 sine 2t means, here if you again compare this equation with this general form, so you see omega, the value of omega equals to 2, so that means f will be equals to 1 by pi, and the amplitude a is equals to 2, and the value of phase is equals to 0. Now, so these are like so if you have this function xt, so you have represented them in the frequency domain in terms of the frequency. So you have two components. One is that t plus pi by 3 component. The another is the 2 sine 2t this thing. So now how would you represent? So now if you want to draw the signal in the frequency domain, so you have, so what we'll do is that in the frequency domain, so you will have two, so here you will plot, in one you will plot the value of the magnitude. So let's say the value of the magnitude is x, and then in another you will plot the phase of the signal, that is, and here you are plotting omega, or let us say you are plotting f. You can even write omega, just that this values will change. So let us say that f we consider 1 by pi, then we have 1 by 2 pi, then we have 1 by 3 pi. Similarly, here also we have 1 by pi, 1 by 2 pi, 1 by 3 pi. So if you go to the previous here, you see that for the first term, so f equals to, at f equals to 1 by 2 pi, the amplitude is 1 and phi is, the phase is pi by 3. So we can write that f equals to 2 pi, the amplitude is so it is having a value of, let's say, 1, and the value of this thing is pi by 3. Right, and then you have the another component which corresponds to f equals to 1 by pi, and at frequency f equals to 1 by pi, the amplitude is 2 and the phase is 0. So you at 1 by pi, you can draw the signal like this. So this is 2 and here this is 0. So you can see that the signal that you have xt equals to sine t plus pi by 3 plus 2 sine 2t. So it has two frequency components. One is at f equals to 1 by pi, and the other frequency component is 1 by 2, f equals to 1 by 2 pi. So this is basically the frequency domain representation of this system. So if you represent x omega, frequency domain, and sigma omega, so this is the frequency domain representation. So you see there are two components. For each component, two frequency components. For each frequency component, you will draw both the magnitude as well as the phase, and you will get this kind of a, you can say, a sort of a, it looks like a discrete representation. And for other frequencies like 1 by 3 pi, 1 by 4 pi, so there are no components of, so omega has only two values in this equation. So one is 1 and another is 2. So the other values of frequency like 1 by 3 pi or 1 by 4 pi, those things does not come into the picture for this equation. So that means the values of both x omega and phi omega will be 0 for all other frequencies. Similarly, if you have a different equation where you will have more than two frequencies, then depending on what is the magnitude as well as the phase, you can draw the frequency domain response, or rather the frequency domain, you can represent that signal in a frequency domain graph like this. Okay, so why do we need to do this domain transformation? So first of all, a given function, it can be so how do we convert a time domain signal into frequency domain signal? So here you see that we will be using Laplace transform to convert a time domain signal into a frequency domain signal. So any time domain signal, it can be represented it can be represented as a summation of sinusoids of various frequencies. So this is like in Fourier series and Fourier transform, it is given that any signal in the time domain, it can be represented as a summation of sinusoids of various frequencies. Now, why do we prefer sinusoids? So because let us say if you have some linear time invariant system you have. So you have your output, this is your input. So you can have a sinusoidal input to this system, you can have a square wave input to the system, you can have multiple types of input. But why we prefer a sinusoid is that because when a sinusoidal signal is passing through a linear time invariant system, then at the output there are only the magnitude and the phase of the signal will change. So if you have, let's say this is some a sine omega t is the input. So at the output you will get something like, let's say, a dashed sine omega t plus phi. Okay, so after passing the sinusoidal signal through the linear time invariant system, only the magnitude a dashed and phi, the phase, these two things change. The frequency of the signal, that remains unchanged when we are passing the signal through the LTI system. But if you use a like a square wave or a pulse kind of thing, then it is the output will not be, the representation of the output will not be as simple as that for the sinusoid. So now a signal can have, so that's why we usually prefer dealing with sinusoidal signals rather than any other kind of signals. So a signal basically it will have character. So if you have a signal is given to you which has some characteristics which is changing with frequency, so then if you want to analyze that kind of a system, or the effect of the a system on that kind of an input, then if you use a frequency domain, if you represent the function in the frequency domain, then it becomes easier for you to analyze the system compared to when if you are dealing with the time domain signal. So depending on what kind of analysis you are doing and what is the transfer function and what is the input-output relationship that is being provided to you, depending on that you can either deal in the time domain where you can represent the system in the differential equation model and then analyze the system, or you can even move to the frequency domain signal where you are representing the system in form of transfer function or in Laplace domain, and then you are from there you are analyzing the system. Okay. If you talk about the transfer function, so in general you can represent a transfer function as, so if you represent the transfer function as GS, so GS will be equals to the output is C divided by the input which is R, and let us say that we represent it as a in this polynomial form. So you have b0 s to the power m plus b1 s to the power m minus 1, so on and so forth, and in the numerator, in the denominator you have a0 s to the power n plus a1 s to the power n minus 1, and it continues. So here so in this polynomial form it can be expressed, each polynomial, this numerator polynomial as well as the denominator polynomial, they can be simplified and they can be expressed as product of individual terms. So this b0 is to the numerator polynomial can be represented by something like k dashed s minus z1 s minus z2 and dot till let's say s minus zm. Similarly, the denominator can be represented by s minus p1, s minus p2, so on and so forth till s minus pn. So now, so these are like two kinds of representations of a transfer function. You can either represent it in using a polynomial form, or you can represent it in terms of product form, you can say. Okay, so if you see this product form, then or from the polynomial form, the highest order of s which is there in the denominator, that is known as the order of the system. So if you in the denominator you see that the highest order of s is n, so that means n is known as the order of the system, and k, if you represent it in terms of like some constant k into this thing, so then k will be defined as the system gain. And when you represent the system in a product form like this, so in that product form you see in the numerator you have the terms s minus z1, s minus z2. So this z1, z2 till zm, these are known as the zeros of the system. Why they are known zeros of the system? Because that if you substitute s with the value of z1, so then the overall system, the magnitude of the system goes to 0. So that's why the roots of the numerator polynomial, that is known as the zeros of the system, and the roots of the denominator polynomial is known as the poles of the system. So at the poles of the system, the magnitude of the system goes to infinity, and at the zeros of the system the magnitude becomes equals to 0. Now if you have in general the value of the number of poles is either greater than or equal to the number of zeros, so that is that is the general norm or convention that is usually there. But in case if there is a system where the number of zeros is more than the number of poles, then in that case the system, it becomes non-causal and those kind of systems cannot be realized. Physical representation or physical realization of those kind of systems is not possible. So in all kind of control systems or systems that we will be dealing with, everywhere you will see that the number of poles is greater than equals to the number of zeros. Okay, so is it any doubts till now?
No, ma'am.
Okay, so a little bit more on the definition of the poles and the zeros. So as we had just told, that poles means the roots of the denominator polynomial of a transfer function, that is known as the pole of the system, and or it can be represented like the value of s at which the transfer function becomes unbounded. Transfer function becomes unbounded as means that the magnitude of the transfer function becomes equals to infinity. So limit s tends to if pi is one of the ith pole of the system, then you can write limit s tends to pi, gs will be equals to infinity. Similarly, for a zero, so zeros are basically the roots of the numerator polynomial of the transfer function, and the value of s at which the transfer function vanishes or goes to zero, that is known as the zero of a system. So limit s tends to zi, gs will be given by 0, and this pole and zero along with the gain, that can be used to characterize the input-output dynamics of a particular system. So now let us take that. Let us do an example. So let us say that there is a transfer function which is given by. So let us say this value of gs is given by 6s plus 12 divided by this thing. So now how do you want to, and if you want to figure out what is the gain, what is the pole and the poles and the zeros of the system, then what you need to do is that first of all you need to express this in terms of this product form. So you need to find out the roots of both the roots of both the numerator as well as the denominator, and then from there you have to figure out what is the gain as well as the poles and the zeros. So from the numerator you can say that if you take 6 common, so 6. So for poles, to determine the zeros of the system, the whole thing goes to 0. So that means 6s plus 12 will be equals to 0, and that will simplify as s equals to minus 2. So that means the 0 of the system is at z1 equals to minus 2. And if you want to figure out the poles of the system, so poles of the system means the denominator will be equals to 0, and gs will be infinite means the denominator will be equals to 0. So now if you say that s cube plus 3s square plus 7s plus this thing, so this becomes equals to s. So if you solve this equation, you will find that there are 3 poles which are present. 3 poles because this order of this equation is 3. So that means there will be 3 roots of this equation. So the roots are s equals to minus 1. Then the other root is minus 1 plus 2j, and the third root is minus 1 minus 2j. So you can see from here that there are the poles or the zeros of a system. They can either be a real number, it can be a complex number, or it can be complex conjugates also. It is not necessary that a pole or a zero should be a real number. So it can be either a real number or complex conjugates. So if it is a complex number, then obviously it will be in a pair like this. So this complex conjugate pair will always be there if in case there is one complex pole or zero present, because the transfer function, the coefficient of all the terms in a transfer function we are dealing with, those are real numbers. That's why either you will have real poles or zeros, or you will have complex conjugate poles or zeros. So now coming to some properties of transfer function. So the transfer function, as you have seen that so gs was represented by ys by xs. Okay, so as you can see that it is a ratio of the output to the input. So you can say that it is independent of the nature of the input that you are providing. So if you are providing let's say you are providing a step input, so then you will have some kind of output y. If you are providing a ramp input, for that you will have a different kind of y. But since you're taking the ratio of ys by xs, so that means the nature or the magnitude of the input that you are providing, the transfer function is actually independent of the magnitude and the nature or the type of input that you are providing. So the response of the system, so what is the beauty of the transfer function? And so why do we need to know this transfer function? Because if gs is known to you, so you can write ys is equals to gs into xs. So from here, if you have if you provide different, so this value of gs is known to you and you want to find out what is the value of ys, and you are giving a specific input. Okay, so if you know the input and the transfer function of the system, then easily you can find out what will be the output of the system, and so the response of the system for various inputs can be studied in order to understand what is the nature of the system and how the system is responding for different kinds of inputs that you are providing. But one thing that in case of a transfer function, what we need to understand is that the transfer function, it does not provide any information about the physical structure or interconnections of the system. So there might be a case where there are two different kinds of physical systems, but they can have the same transfer function. Okay, so for example, let us take this example of this spring mass damper system. So in case of a spring mass damper system, so this F was equals to, for this, so F was equals to m into x double dot plus b into x dot plus k into x. So if you take the Laplace transform, so Fs will be equals to ms square xs plus bs xs plus k into xs. So if you write xs by fs, this will be equals to your gs. So that is given by 1 by ms square plus bs plus k. Now if you have a system where the value of m, b and k, those are 1, then your transfer function of the system becomes 1 by s square plus s plus 1. Okay, so this is a mechanical system whose transfer function is s square plus 1 by s square plus s plus 1. Now similarly, if you have a series RLC circuit, in case of a series RLC circuit, you have the transfer function is given by 1 by LC. So this is not k, this is 1. So the transfer function is the generic transfer function is given by 1 by LC s square plus RCS plus 1. Now if you have the value of L, R and C are all equals to 1, so that means the transfer function becomes 1 by s square plus s plus 1. So you see that in both this system, this mechanical system as well as this electrical system, the transfer function remains the same. But this same transfer function, it does not necessarily mean that both the systems are the same systems. This is a mechanical system which is completely different from this electrical system. So basically this transfer function, it does not represent, or it does not provide any information about what kind of system is actually present, whether what is the physical structure of the system, whether it is a mechanical system, a thermal system, electrical system. Those kind of information is not being provided when you are dealing with the transfer function. But what we can do using transfer function is that if you have different kinds of inputs, if you provide a different types of input to the system, then you can generate, or depending on the transfer function, you can find out what will be the output of your system, given that you are providing a specific type of input. Okay, so now there are some steps or procedures which we need to follow while deriving a transfer function. So before deriving a transfer function, there are certain assumptions that always need to be taken care of or kept in mind. So first assumption is that there should not be any loading in the system. So that means no power should be drawn at the output of the system. So now let us say that if you have, so no power is drawn means that if the system has more than one non-loading elements. Okay, so if the system consists of two non-loading elements which are connected to each other, then what you can do is that you can take the transfer function of, so the overall transfer function of the system will be equal to the multiplication of the transfer function of each element, which can be determined independently. But this thing will be only valid if it has, the components are not non-loading. So both the components are not loading each other. In that case, you can derive the overall transfer function of the system just by multiplying the individual transfer functions. But what happens if there are two elements which are loading each other? So two elements are there is the second element which is present, that is actually loading the first element. In that case, you cannot use this just multiplication of this individual transfer functions. What you need to do is that you have to go back to your basic analysis. You have to write the differential equation model, and from that differential equation model, you have after writing that basic differential equation model, you have to take the Laplace transform, and from there you have to step by step follow and find out what is the output by input, that is the transfer function. Okay, so this is something which always needs to be taken care of or kept in mind, that multiplication of individual transfer function, that is only valid if the components which are present or those are not loading each other. Okay, so also another assumption is that the system is usually approximated by a linear lumped constant parameter model. We are not dealing with distributed parameter model, and then we can derive the transfer function of a system. So let us in order to clarify what we had seen just now. So let's say that you have there is a cascaded, there's a system where there are two RC circuits. So R1 and C1, then you have R2 and C2. So let us say if the input voltage is EI and the output voltage is E0, and let's say the current which is flowing in the first loop is I1, and that in the second loop is, let us say, it is I2. So if in general it might, so if you take this as your system, subsystem number 1, this is, let's say, your subsystem number 1, and this is your subsystem number 2. This is subsystem 1, this is subsystem 2. Okay, so it might, apparently it might look like that, okay, if I get the transfer function of subsystem 1, if I take the transfer function of subsystem 2, and if you just multiply these two, we'll get the overall transfer function. But will that be the case? Let us see. So here you see that the first part of the system, that is the subsystem 1, that is actually being loaded by the second part. Okay, because of this loading, so if you take the individual transfer function, let us say if the values of R1, so let's say if R1 equals to R2 equals to R, and C1 equals to C2 equals to C. In that case, the transfer function of this turn of the first series RC circuit will be equals to 1 by 1 plus tau s, where tau is equals to RC. So it might seem like if I just multiply these two, so 1 by tau s into another, this is also 1 by tau s. So ideally it should give a transfer, the overall transfer function should be 1 by 1 plus tau s whole square. Now let's see whether that is the case or not. So if I write the basic differential equations, so then if I apply a KVL in the first loop, then we can write that 1 by C integral minus infinity to t, the current flowing through this capacitor is I1 minus I2 dt plus R into I1 is equals to E1. Similarly, if you write the loop equation in the second loop, that will be given by this equation. Now, so these two are the basic differential equations of this system. So now if you take the Laplace transform of both the equations, so the first equation, the Laplace transform comes as 1 by SC I1 minus I2 plus RI1 equals to EI. And then from the next equation, you have Laplace transform, you have this equation. Okay, so now if you want the transfer function, so the transfer function will be the Laplace transform of the output, which is E0s, divided by the Laplace transform of the input, which is EIs. So from these two equations, you see that the value of Gs will be equals to 1 by tau square S square plus 3 tau S plus 1, wherein tau is equals to RC. Now you see that here the value of the overall transfer function, this is obviously not equal to 1 by 1 plus tau S whole square, right? So why this is not equal? Because the second stage, this is the second stage that is actually loading the first stage of the system. So our basic assumption that the two elements or two stages of the system should be not loading each other, that is not being satisfied. So if that is not being satisfied, so that means we cannot just use the term, we cannot just multiply the individual transfer functions in order to get the overall transfer function. You need to find out what is, you need to start from the basic differential equation, and from there you have to take the Laplace transform and then subsequently find out what is the transfer function, what is the ratio of the output to the input. Let's see that, so this we had actually already talked about, like how the transfer function of a Spring-Murs tempered system looks like. So here it is 1 by ms square plus bs plus k. So now since the denominator, the highest power of s is 2, so that means the order of this system is 2. So means that the Spring-Murs tempered system is a second order system. You take the thermal system. So we had talked about how the thermals, the differential equation. So this was the differential equation for almost a perfect system with no losses. With no loss, like perfect insulation, that kind of a system. Here, if you, so this was the differential equation representation of the thermal system. So you take the Laplace transform, and there from there you will find what is the transfer function, which is the output delta theta s by the input, which is delta hs. So here you see that for this ideal thermal system, this is the first order system, since the power of S is the maximum power of S here is 1. So that means the thermal system, that is a first order system. Similarly, you can find the transfer functions for different liquid level systems. So this is a liquid level system that we had talked about in the last class. So here also you see that if you just have one liquid, a tank, and there is an input and the inflowing of liquid and outflow of liquid. In that case, the output by input is given by 1 by RCS plus 1. So this is also a first order system. But in case if you have like an adjacent connection, so there are like two tanks. So one tank is this, and the output or the outflowing liquid from this tank, that is actually going as the input of the second tank, and there is another output. So from there, if you have like this kind of a cascaded system or a system with interaction where the output of one system is acting as an input to the second system, then if you write the, so here actually you see that since these two are cascaded system, so that means you cannot just take the transfer function of system 1 and system 2 and multiply them. That will not give you the overall transfer function. You'll have to start from the basic differential equation, and from there if you see the final transfer function, you see that the order of the system now gets increased and it becomes a second order system. So the main thing for deriving a transfer function is that you start from the basic differential equation and then you take the Laplace transform and find the transfer function of the system. Now let us talk about transfer function of a DC servo motor. So if you have a DC servo motor, which is, so in this case, let us say that we have an armature controlled DC servo motor. Okay, so here you have, so there is this, so let us say that the resistance of the armature, so this is the armature side, the resistance of the armature is RA, the corresponding, the inductance of the armature winding is given by LA, and the input voltage that is applied is given by EA, and this is the motor that we have. and similarly, there is a field current on the other side. So this field current is actually kept constant, and because in the motor there will be a back EMF. So if you have all these terms and then you, so mostly a DC servo motor, when they are usually generally they operate in the linear range of the magnetization curve. So in case of in that linear range of the magnetization curve, the air gap flux which is produced here, that is given by phi, that is usually proportional to the field current which is flowing. So, and the field current is constant in this case, so phi is given by kf into if. And the torque which is developed by the motor, that is actually proportional to the product of the armature current as well as the air gap flux. So you can write that the torque generated in the motor Tm will be proportional to this phi, and it will be proportional to the armature current which is Ia. So Tm is proportional to phi and Ia. So you can write Tm will be equals to some constant. You can represent phi as Kf into If, and there is some proportionality constant K1 and Ia. So from here, and since If is constant for this armature controlled DC servo motor, so that means Tm will be directly proportional to the armature current. Now the back EMF which is produced by the motor, that is actually proportional to the speed of the motor, and that is given by this equation EB equals to some constant K into the rate of change of the angular position of this angular position. So from here you can write that if you take the first this loop, and you can write the differential equation. So you will have the current Ia is flowing, so the voltage drop across here is Ia into Ra, then across the inductance it is La into dia dt, plus there is some back EMF in the motor which is equals to Eb. The overall everything will be equals to Ea. So this is one differential equation, and then you can write the torque equation also, which is given by this. So once you have these two equations, these two differential equations, now what you will do is that we'll just take the Laplace transform. So actually we have three equations. This is equation number 1, this is 2, and this is 3. So there are three differential equations. You take the Laplace transform of all the three equations. So this, and from these three equations you calculate what is the value of the transfer function. So the transfer function will be what is the output of my system. Output of my system is theta, which is the angular displacement of the motor, and the input of my system is the armature voltage that I am providing. So that means GS will be equals to theta S by EAS, and from these three equations you can write. So this will be the transfer function of this of this armature controlled DC servo motor. Okay, so similarly, if you look in the field control mode of the servo motor, of this DC servo motor, there what is happening is that the field current that is actually varying, and we are getting, and the armature current is kept as constant. So this armature current, this is kept constant, and so armature current is fed from a constant current source. So the torque which is generated, that is directly proportional to, you can, in the previous case we saw that the torque was proportional to the armature current since the field current was constant, and in this case the armature current is constant, however the field current is varying. So the torque which is generated by the motor, that is proportional to the field current. So then if you write again you write the loop equation in this loop. So you have LF dIF dt plus LF dIF dt plus RF into the current IF, it will be equals to the field control voltage that we are providing, which is equals to EF. And then similarly you can write the torque equation, and here in case of a field control DC servo motor, similarly the output is here also, it is the same. The output is theta, that is the angular displacement of the motor, and the input here is the field voltage that we are applying, which is EF. So the transfer function will be given by theta S by EFS, and that is given by this term. And you see that here, actually, if you see what is this is basically a third order equation, because the highest term of S, or rather the highest power of S in the denominator is, so you have S here, S here, S here. So you have, this is a third order kind of an equation. So this is like the how to derive the transfer function of different kinds of systems. And then comes the concept of block diagram. So block diagram is nothing but it is a pictorial representation of functions which are being performed by each component of a control system. So you have, so we have right now, till now we have been talking about something. So we talked that this is an LTI system. So this is basically, this square is basically a block. Okay, so this block basically it defines the functionality of the system. So it depicts the interrelationship, and you can represent the system. If you know the transfer function of the system, from there you can depict the system, the interrelationships between various signals which are flowing into the system. So if you remember in the first class we talked that a system can consist of several subsystems also. So each subsystem can be represented by a block, and the interconnection of these blocks, that will constitute the overall system. So this block diagram basically shows how all the system variables are connected to each other, or how they are dependent on other system variables. So this functional block basically it shows the mathematical operation that is being performed on the input. So if you have this input X and output Y, so the mathematical transformation or the mathematical operation which is performed on the input to provide the output is given by this block. So usually in a block diagram, the transfer function is entered in this functional block, and each block will be associated with a flow of the signal. So it will be associated with the input flow of the signal as well as the output flow of the signal. Now, if you let's in the previous case, just now we saw that for this armature controlled. So in this case, armature controlled DC servo motor. So we saw that there were like three differential equations, main differential equations were there, right? So these are the three differential equations. So let me write those equations over here. So one was EBS is equals to KBS theta S. The second one was okay. So and GS was equals to theta S by EAS. So now if you want to represent this first equation, okay, so the first equation you can write that if KB is your, so you have this, so if you represent this block by as KB, or rather as KB into S, so the input to this one is actually equals to theta S, and the output will be represented by EBS. So this equation can be represented in this way. So input is theta S, multiply it with the transfer function KB into S will give you the output EBS. Now let us see the second equation. The second equation you have on the right hand side, you have one. So there is a comparison. So you have EAS, and then you have EBS over here. So EAS minus EBS will be equal to so if you have 1 by LAS plus RA, and the output is IAS. So you can write that if output is IAS, so that means IAS it will be equals to EAS minus EBS multiplied by 1 by this term. So you can represent this in terms of EAS minus EBS, then you have 1 by LAS plus RA, and you have this third. So this is another part of the block diagram. Okay, and if you want to represent the third equation, so the third equation will look like you have theta s as your input, or rather so you have KT. Yes.
Ma'am, could you continue in next class, ma'am? Our other class has started.
Oh, okay. Sure. No problem. We'll continue this in the next class. So actually, tomorrow and day after tomorrow, we'll not have any classes. So I'll take a makeup class on next Tuesday at 2:30, and then again Wednesday at the scheduled time 11 o'clock we'll have our class. Okay. So tomorrow and day after tomorrow we'll not have any classes. I'll post it in the group for your information.